Slim. I'm the Director of Product at Social Hackers Academy. Today we are thrilled to have with us Leonidas and Nazaret from Upstream Systems for the presentation about microservices. So this is a very interesting topic, but before jumping to the topic, let me tell you a bit about Social Hackers Academy, SHA for short. So we are an online bootcamp, coding school, let's say. We are operating since 2017. So we had our sixth anniversary on the 4th of September this year. And what we do is, our mission is to make tech education accessible to everyone by teaching full stack web development and some other programs from here and there, like blockchain, like the AWS restart program at some point we did. And and we are trying to support a vulnerable group of people like refugee, asylum seekers, and we are expanding our target groups by providing free scholarships. So yes, making tech education accessible to everyone, non-formal education, of course. And that's pretty much it. And today we have Nazaret and Leonidas. So if you would like to present yourselves, guys.
Thank you, Slim. Hi, everyone, and thanks for having us. My name is Nazaret Kazarian. I'm the VP of Engineering at Upstream. And Leonidas.
Hello, also from my side. Thank you, Slim, for having us, and I also want to congratulate you on your work. I'm Leonidas Patouchas, and I'm Director of Engineering here at Upstream.
Nice to have you with us, guys, and thank you for your time and for making this happen. All right, so maybe, hi Sandra and hi Emre from the chat. Thank you for joining us today as well. And maybe let's jump into the today's topic. So let me add the screen share to the stage, and we are good to go.
All right. So welcome to this session. This is going to be about microservices, this interesting topic. I'm sure you have heard this term many times. It's a quite hot topic. It's been around almost 10 years, so I wouldn't call it a hype. It's more something that has gone through the stages of, early excitement, hype, and maturity. So we will discuss this architecture mostly from the point of view of our experience as we have applied it at Upstream for the past almost 10 years. Upstream, let me tell you a few words about the company. So Upstream is a leading marketing technology platform company. We offer a multi-channel customer engagement for companies in various industries. We are focused on markets with high growth potential, like Latin America, Africa, Asia. We have people across 30 nationalities, employees, and we have offices in 7 different cities. Our flagship product is called Grow, and it is built with the microservices architecture. So that is what we will mostly focus on today. So we will we will compare the microservices with monoliths. We will compare the benefits and the challenges of those two architectures. And as I said, mostly we will give you some insight from our experience implementing and applying these architectures throughout several years.
Yeah.
Leonidas will please start the presentation.
Yep. So Nazaret talked about microservices, and we're going to discuss about them. But before microservices came, we had the monolith. If someone has heard this word, what are monoliths? What applications do we describe as monoliths? Monoliths are a monolithic application. Is an application that is a single application. It's unified, large, and standalone. For large projects, monoliths tend to have a large and single code base, one repository, let's say one Git repository, that covers the full functionality of the project. This also leads to have a unified technology stack. This application, its code base is on the same tech stack, for example, Java, .NET, etc. And most of the times, it also has a single database that holds all the application data. We will elaborate on that later on. Having a unified tech stack and single deployment on a same physical machine and single database, all these aspects tend to lead to a tight coupling set up on monolithic applications. So in a nutshell, this is what is a traditional monolith. So where we had some issues with the monoliths we had to deal, and what are those problems that we faced in here in Upstream with the monolithic architecture. This larger code base that we have, our application covers all the business functionality of all the business functionality that needed to be implemented, and that leads to a very steeper learning curve that has as a result to be more difficult for new developers to join the team and be productive fast, since they had to maneuver themselves in this larger code base. Also, since we have a large code base in a monolith, we tend to put more than one functionality in a single component, since communication among all, let's say, functions of our application is much easier. So although it shouldn't, it leads to some kind of anti-patterns. Moreover, the scaling is more difficult. We have vertical versus horizontal scaling. It's difficult to scale independently. Vertical scalability is easier. Vertical we mean adding resources, extra cores, extra memory, etc. Horizontal in a monolithic application might not be achievable at all, but if it is, it's not efficient, since we will scale the entire application, and the entire application has to scale. Moving to deployment, as you can understand, since we have one single application, we will deploy everything or nothing. And having this setup, if we have an issue to a minor functionality that is not that important and our application cannot start it will prevent it from work, the full application, it will prevent it from work. This might lead to downtime that in other cases, let's say in a microservice setup, could have been prevented. Technology stack. As we mentioned, we have to choose wisely the application technology stack, since monoliths tend to have a single technology stack, and migrating from one to another, it's holistic. We have to change the whole application. It's not that easy. Moreover, resilience. If one component fails, it can bring down the entire application. We talked before about problem during deployment, that it might lead to downtime, but it can also have a bug during the runtime of our application, or an infrastructure issue. Let's say, for example, a load to a specific service. When I mean service, I mean a specific business part of our application, or a hardware failure. Since we have one single deployment, this will lead to downtime to our whole application.
Okay. So we mentioned all these issues with monoliths, but does that mean that this architecture doesn't work, or we should never use it? Not at all. Actually, as upstream, our platform was built as a monolith until 2014, and it was working just fine. At some point, the company started growing in very large numbers, and this business growth, this organizational growth, the teams were expanding, more teams were creating, and our architecture, our software architecture, had to adapt to enable this growth. So this is where this was the point where we decided to introduce the microservices concept, which was actually in the quite. It was at the time where it was recently introduced in the software community. So what is microservices? Microservices, well, we identify and break down the application to separate business functionalities. And we can have different teams work on different business functionalities. This means we can have different code bases per team. Each microservice is a separate deployable standalone application. So it's not a library, it's a standalone application. Communication services, since they are standalone applications, they cannot natively talk to each other, so they need to communicate via APIs, message brokers, or a combination of both. We have each service have its own database, and each service can have its own release lifecycle. So it can be developed, released, and deployed independently. All this is, of course, transparent to the end user, because it's just the software architecture. It shouldn't affect how the product is perceived from the end user. So all services are combined and provide the same functionality as the monolith did.
So this was, let's say, the definition of microservices, some key points of what microservices are. But what are the benefits that we get with a microservice architecture? If we could summarize the benefits in the microservice world in one word, it would be independence. As Nazaret said, the teams now can work independently, and our services can be developed and run independently. We will see later on how we can achieve that. Having a smaller business scope per microservice leads to teams being more focused in a specific business functionality, and this can make them more productive and much more focused, and they don't have to deal with the clutter that sometimes monolithic applications have. Also, having smaller application scope means that our teams and the developers can be more efficient. And since we have smaller scope, we have faster onboarding. That it's something opposite to the monolith that we mentioned before. Since the new developers don't have to learn everything and all the ins and outs of our application, and can be much faster productive. Also, since we have independent services for each function that we have identified before how we will separate those functions of our applications, we can identify easier and faster bottlenecks that don't let us scale, and scale only those services that we actually need. If you remember, we said before that we can scale also a monolith, but we have to scale all the application or nothing. Now we can have a more specific approach and scale only the services that we need. This can be achieved either by horizontal scaling or maybe by a different technology stack, since we can have a different service and different deployable per microservice. We can identify that the technology stack that we started has some limitations, and we can easily switch it only for the specific service. If this sounds vague, you can imagine we can choose from different databases, from traditional RDBMS to NoSQL databases, or even obviously different programming languages. So this technology flexibility is a clear benefit of microservices, and it's much faster to achieve it in this setup. As we have already mentioned, each service has its own release cycle, life cycle, and combined with the higher developer productivity due to the reasons that we have already mentioned, we can achieve higher time to market, what we say, meaning identified bugs, new features, reach the final customer happy. So happier customers and happier product managers, I will say. Moreover, each of our microservices are isolated from some possible unhealthy sibling services. Failure of one component does not necessarily risk our entire system. By failure, imagine some resource starvation or memory leak. If we had this kind of issues to a single monolith deployed on a server, most probably all the aspects of our application would not work. Here with microservices, we can narrow it down to specific service that might have these issues. So everything sounds perfect, but it's not, obviously. It's not a perfect world. So microservices also come with a lot of challenges. By definition, microservices are a distributed system. And by definition, again, distributed systems are more complex, make everything more complex. Since we broke our monolith, now there's a network communication in order for our new services to talk with each other. So naturally, we have to account for some possible failures, higher latency than before, and this might lead to some issues. Also, there is a need for coordination between those services, And in general, there are much more moving pieces that they need to cooperate. So this adds a complexity that sometimes is more cumbersome to tackle. Also, having multiple databases, it's harder to maintain data consistency. This is a big issue on microservices. So a single relational database that a monolith had offers atomicity, consistency, isolation, and durability, also known as ACID. You may have seen it. However, in microservice architecture, since everything is distributed, they are more geared towards the base model, meaning basically available and eventual consistent. So not that you cannot achieve ACID through microservice, but it's much more difficult and has lots of challenges. So if you are looking for very, very strong data consistency across systems, microservices are challenging to achieve that. Regarding testing, again, as we mentioned before, more moving pieces. We have more moving pieces, and that means it's harder to test the end-to-end functionality. Imagine if you have a monolith, you can even easily start it on your local machine and start doing some manual testing. Now we're talking about multiple services. Sometimes there can be more than 10 in a real production application environment, can be more than 100. It's natively more difficult to do this locally. So the hardest part is when all the services are integrated and you need to do some tests that all of them need to work together not to provide the end result. As you can understand, if something goes wrong, troubleshooting is also more complex. As one business flow typically involves multiple microservices, and we need to check that the actual business flow across different modules works okay. And sometimes we might have different technology stacks. So to identify an issue is more difficult than the monolithic application. Also, microservices, I have mentioned more than once that we have more services that talk with each other. They have a large operational overhead as well. There are many more servers involved. The logs are scattered. Our data are scattered to multiple databases, different database technologies. A new installation of microservice environment can involve very large effort and very large numbers of servers and our application deployments. So this is a bit cumbersome. All these issues that I mentioned, we're going to talk in the next slides how we can surpass them by following some common microservice practices.
All right, so here are some common microservices practices to tackle the challenges that Leonidas mentioned. And these are the practices that we have actually followed at Upstream in our implementation. Firstly, when breaking down the system into multiple microservices, we need to think very carefully about the boundaries of each service. This is far from obvious. It might sound easy, but in a real system, it really isn't. And it's a very important design decision, which is hard to change later. The guide here is to analyze the various distinct business domains that in the overall system. So separate each business domain into its own microservice. And that is what we have done. There are other approaches that may further break down into much smaller microservices, but it's not necessary. And since each business domain is a microservice, we can easily agree that we should have a separate database, as Leonidas mentioned, for each microservice. This also enables us to use a different database technology depending on the needs of each service. For example, we have used multiple NoSQL databases in our services depending on the exact problem that each service had to solve. Then, as we mentioned, each microservice is a standalone application, and it can even be implemented in a different technology stack. So we need a way to communicate between them. A very important step in our software design process is the design of our APIs. As we will see in a later slide, we can communicate, the service can communicate either synchronously or asynchronously. We introduce a concept called an API gateway, which orchestrates the services, as well as a message broker, which can move messages between the services. Then test-driven development is necessary to ensure the quality of the deliverables. At Upstream, we perform automation tests on many levels, starting from the unit tests that the developers write, and we also write integration tests, performance tests, deployment tests, security penetration tests, and so on. All these automation tests enable us to perform a CI/CD process, continuous integration, continuous delivery process, which enables us to have weekly releases and deployments across all our production environments. So quite fast time to market for a new feature or a bug fix to reach production. Another common practice that we also follow is called distributed tracing. This means we need to have a common identifier, like a transaction ID, across all our microservices. And every logging includes this transaction ID. This is necessary for troubleshooting these kinds of complex systems. And there are specific tools and libraries that enable this. Now, due to the distributed nature of data in a microservice architecture, remote communication is inherently slower. So there is often the need to cache some data on each application to avoid the extra communication overhead. For this, we use several technologies like Hazelcast, Redis, Memcached, and so on. We have both centralized and distributed caching solutions, but I will not expand more on that, as I think it could be a presentation on its own. Other microservices practices is service discovery. So what's that? Given the dynamic nature of the modules, like the servers, which can start and stop dynamically, or new microservices may be added, we need a way to discover those various services and servers. And for this, there are off-the-shelf tools, as well as custom implementations. And this is called service discovery. Now, since we natively have multiple servers and nodes, we need to distribute the traffic evenly on all of them. So we should basically avoid sending the entire load to a single server, and definitely identify faulty servers or servers that need to be shut down or restart due to maintenance. So load balancer enables all these to distribute the load evenly and to allow for a server to restart and not receive traffic while it's restarting. This enables zero downtime deployments. So all our updates and deployments don't have any impact on the live traffic, which can go on, and the update happens seamlessly. Load balancing can be achieved either via software or via hardware load balancers. Now, each service is on its own silo. As we said, independence, isolation is very easy. It should be very easy to set up an application locally as well for development or QA. So the application server, the databases, the message broker, we need to have a very easy way to set these up. So here at Upstream, we from the first day that we decided to transition to the microservices architecture, development teams and quality assurance used Docker containers for this purpose. And further, in the following years, as orchestration tools became more popular and mature, we started using Kubernetes, which is an orchestration tool to manage all the operational mess, let's say, that the complexity of the microservices brings. We use Kubernetes on our production systems, and it provides features such as auto-scaling, of course. Like if you have more traffic coming in, it will automatically spin up new nodes of the applications and do the reverse when the loads decrease. It provides load balancing as well, and resilience. Like if there's something wrong with one server, it will restart it automatically, and so on. Now, managing a large number of services requires elaborate monitoring of the system with regards to its performance, the uptime, potential issues, bottlenecks, and the health in general. So we use enhanced monitoring and logging tools. Tools such as Prometheus and Grafana. So we have invested a lot in the observability of the platform. Centralized logging is also a common practice, for example, using the Elastic Stack. To implement all the above, a very important practice is what is called infrastructure as code. What that means is that all the topology, the infrastructure topology and configuration is kept in version control, just like our application code. So we don't set up an environment manually and install software manually. Everything is versioned as code and is run automatically. In recent years, another popular software practice is what is called cloud native. And this has a lot of common ground with microservices, as all of the above mentioned practices are also necessary to make an application cloud native. Cloud native means cloud friendly, let's say, able to run in the cloud, either private or public cloud. For example, having small, flexible, standalone applications, which can be easily bootstrapped, is essential for application to be considered cloud native. And indeed, we run our production systems both in a private cloud that we maintain, as well as public cloud providers. All the above boils down to heavy investment into automation. We strive to have everything automated, like server provisioning, tests, releases, deployments, and even failure recovery.
Now, regarding microservice communication, which can also be a presentation on its own, as it's a very hot topic. As we mentioned above, we have multiple services, multiple servers, and separate applications and processes that they need to communicate with each other. This communication can be done either synchronously or asynchronously. With synchronously means that the caller waits for the response before processing anything else. And asynchronously means that the caller sends the request without waiting for the response, and sometimes without even knowing who the recipient will be, and sometimes might, after the fact, gets the response in order to process it in a totally asynchronous manner. Synchronous communication is usually achieved with RESTful HTTP APIs, which is the simplest way, and I'm sure that everyone is familiar with. And asynchronous communication, which is a bit more complex, is usually implemented with message queues, such as RabbitMQ and Kafka, or some reactive technologies like reactive streams and RSockets. In general, we focus on making all communication as loose coupled as possible in order to achieve in the microservice setup this independence that we talked before.
All right. So this was our experience, let's say, regarding microservices. In this slide, I'm sure you're interested. We will show you the most important technologies that we use to implement all of these. So we use React, Next.js, TypeScript, Node.js, and Laravel for our full stack applications. So one microservice may be written in Node and another in Laravel, for example. We use Go for several supportive tools, I would say, that our DevOps teams develop. We use Java with Spring Boot and Quarkus for the core backend of our platform. So most of the backend microservices are written in Java. We use Scala, Spark, and Hadoop for our data engineering, our big data processing pipelines. We use Kafka and RabbitMQ as our message brokers for the asynchronous communication, as we explained. We use Python for automations, the automated releases, deployments, and all those automations. Jenkins is our CI/CD server, running all the automation tests and deployments. Selenium is our tool for test automations, as far as the UI automations. Postgres is the relational database that we use in most of our services. And as I mentioned, we use a lot of NoSQL databases such as MongoDB, Elasticsearch, Redis, and Cassandra for various pieces of the puzzle. And we use Kubernetes and Docker as well, as I mentioned, in production. So let's share a brief conclusion about all this, and keep some time for to answer questions and to make the session a bit more interactive. So the conclusion: should we always do microservices and forget about monolith? I would say definitely not. The key points to always remember is to avoid over-engineering. Keep it simple. I will never get tired of saying keep it simple. Automate as much as possible, because you can't do successful microservices implementation without automation, as we explained. And when in doubt, usually start with a monolith. I mean, you should have a strong reason why to choose a microservice and not a monolith, because it's much more complex. So as I said, our business growth drove us towards that architecture, and not just a software decision. And Leonidas, I don't know if you want to add something on the conclusion.
Yeah, the only thing I would like to add is, if you see the previous slide, it might look a bit intimidating, all these technologies, but every single one of them have a purpose. So I would say that, you start with a basic, let's say a single relation database and a monolith, and if you have identified before some specific problems that that you will face, then you might need to introduce more technologies and even more services. But as Nazaret said, we should keep it simple and identify issues and pains later on, and try to find the proper technology in order to solve the issue that we have, and not choose the technology in order to create something and then later on see that it wasn't the proper solution for that problem.
And with this said, you just answered a question. It was saying, with all this tech stack, isn't it already over engineering? So, because I think in the previous slide, you said like, no, don't over engineer. So you just answered that. So it's not about the. Also from what I understood from what you said, Nazareth, did you start with a monolith and then switch to microservices? Is that the case? Okay. So I think it was the business needs and so on that brought you to take that decision. Okay. So we have a couple questions actually. So first thing, thank you very much for this amazing presentation and for breaking down all these topics. It's very informative and interesting. And the first question is, what's the difference between horizontal and vertical scaling? So we discussed this at the very beginning.
Leonidas, you want to take this question? Or?
Yeah, feel free. Wonderful.
Sure. So vertical scaling is the traditional, let's say, scaling, where you just add more power to the server. You add CPU, you add memory, you just throw it out and get a new server. You basically have a more powerful machine. Horizontal, and that was a traditional way until it got to the point where we couldn't scale further by doing that. And so people invented vertical scaling, which means basically, instead of having a very, very powerful machine, have many not so powerful machines working together and distributing the load. So have maybe 10 machines without each being, a supercomputer. So that is a vertical scaling. And there are technologies that are built to allow that, and there are others that are less, let's say, it's more difficult to adapt to that model.
Okay, thank you.
Clustering, yeah.
Thank you, Nazaret. I think your answer, I think this question is related to another one, which is about load balancing. And the question says, so if services are separated, then why we need the load balancer? Doesn't the load based on how often it's used? I think what the question means. So the balance, I mean, different services. So then we need to balance the load based on how much each service is used. So I don't know if that makes sense.
Sort of, but if I answer this question, I would say that we separate our scope of work into different microservices. This is one part in order to have different servers, let's say, take specific load. But even there, we want to have load balancing in order to achieve better efficiency. We will have like 5 servers, let's say, 5 instances of the same microservices. We don't want the 90% of the load to go to the first instance and all the other 4 instances to sit there and do nothing. So we want to evenly distribute the load of our application in order to be more efficient and more robust. So this is the concept of load balancer. And as Nazaret also said, it's also a way to achieve not calling a service that has been diagnosed, a node that it has been diagnosed as a faulty one. You might have 5 and 1 has an issue, or if you want to do zero downtime deployment and you want to stop the first node and then stop the second and then start it, to achieve this also by the load balancer to stop sending traffic to the servers that they are being restarted. So in a nutshell, to evenly distribute the traffic, the incoming traffic to your specific microservice via sending it to each instance of the server that it is up for this microservice. Hope I answered the question.
I think you did. Thank you very much, Leonidas. And the last question is, what are message brokers in the communication between services?
Okay. What are message brokers is the question.
Yes.
Yeah. So message brokers, for example, RabbitMQ is a message broker, is the software that has all these message queues. So when you have 2 applications that you want them to communicate, you can put a message broker in between. For example, RabbitMQ, you put it in between. The one application sends messages to a queue which is on RabbitMQ, and the other application takes the messages off of that queue. So that way you have asynchronous communication. The one doesn't need to know who is the other, doesn't need to, they don't need to be up at the same time. It can just send a message to the queue, and whenever the other application is available to receive the message from the queue, it can do so. So that is a message broker in a nutshell. Kafka can also be used as a message broker, and others. There are other softwares like Java Messaging Service, JMS, and ActiveMQ, and so on.
Okay, thank you, Nazaret. And we have another question, but this one is more about your users. So the question says, from what industries are most of your business end users?
I'm having a bit difficulty. It's breaking up the audio. I don't know if Leonidas heard, or you can repeat it.
It's from what industries are most of our business end users. I would say mobile operators and also e-commerce applications. But if you want to add something, Nazaret.
Yes, it's our traditional customers were the mobile network operators, and they are a large percentage of our current customers as well. E-commerce, e-shops basically are also a big part. And basically our platform is, let's say, can be useful to any kind of customer, any industry, any advertiser that provides some product or service can benefit from our platform because it is a marketing technology platform that can boost, sales basically. So it's not, specifically geared towards one industry.
Thank you. Guys, I think that was the last question so far. So if anyone else have any other question, you can write it down in the chat. Otherwise, thank you very much, guys, for this amazing presentation and for explaining all these concepts. Just a reminder to our lovely students that it's okay if some of the concept feels overwhelming somehow. You are still at the beginning of the road of the journey, and once you will get into the industry, you will be exposed to these concepts step by step, and by the end of the day, you will be familiar with most of this technology, depending on the company you are working with, the industry, and so on and so forth. So, yeah. Thank you again, Leonidas and Nazaret. It's a pleasure to have you with us. And yeah, I think if you don't have anything else to add.
Thank you, Slim.
Thank you very much for this opportunity, and thanks everyone for your time for attending this. I hope you got something out of it, and for sure there are, we threw many advanced terms out there, but you can, take each one of those and research it by yourself and learn about it. But that's pretty much it from our experience of 10 years of using those. So of course you will not learn it in a week, but the important is, if we got you kind of interested in some of these things, you can read more about them.
Definitely, and just as a reminder, this event is recorded and will be uploaded by tomorrow on our YouTube channel, so you can rewatch it. And if you want to dive deeper in some of the concepts, you can watch again and then use it as a kickstart of any stack you want to dive deeper into. So thank you again, guys. It was a pleasure. Thank you for your time and for making this happen. I hope to see you in another event potentially in the future. Maybe some of the concept that you said that could be a slide by its own. And yeah, I wish you all a lovely evening, and see you very soon.
Thank you. Bye-bye.
Goodbye.
Thank you. Bye-bye.